So let's move to the general topic of what we're doing, because data science is something that is a very rich field. And saying that we can learn about data science as it is very misleading, because it contains so many different stuff coming from multiple areas that you need to get some kind of understanding of different approaches. So that's why in our studies at the moment we separated certain aspects of data engineering into the advanced databases. You have courses of machine learning next semester. You have our course to get your let's say feet wet with statistical modeling. So you will get maybe not be able to do it directly, but you will be able to, let's say, understand things that you want to do later. So not only keras.fit, but do a bit more regarding what is happening in your models. And statistics has a very important part in general data scientist toolbox, because statistics allows us to model certain aspects that are very important and complicated, which is uncertainty. And generally, in this course, we will focus on Bayesian data analysis and statistical modeling, because, which I'll try to explain today, of two possible options, statistical modeling, only Bayesian option is reasonable for any kind of practitioner. But that causes us that our models will be grounded in probability. So we will have to see some math here. So be prepared that certain integrals will pop up, certain probability distributions, perhaps differential equations at certain moments. Those things will happen because they are there, and we cannot avoid this aspect because those things happen in the process. However, those models that we are focusing on are as interpretable as possible. This is something that is being, for multiple times, it was being discussed on multiple levels, on decision level, love-making levels, what your model of algorithm is doing. How can you, when decision is being made based on the algorithm, can you retrace why it was made? What was the reasoning that happened? And there are two ways of approaching this problem. One that some people try to traction is explainable AI. Explainable AI is that we create a usually neural model of some kind of deep learning option that you will learn that model using your data. This model will work to certain KPIs you want it to work, and then you will try to retrace how this model works, and most of explainable AI are heat maps. So it shows, oh, this thing in picture worked. Why? It's a heat map. That's it. So this is explainable AI, and it can give you certain answers, not necessary to the question you asked. That's the main problem. And that's why general consensus in the scientific community is that there is a limit what you can get from explainable AI. So other way is, let's create interpretable models. So let's start to create model that works from the other side of understanding the process. So we are adding the elements of the model, and we are complicating the model by understanding what each component adds to that model. This is complicated in cases when we really do not understand what's going on. Because if we want to create a system for image recognition, then unfortunately we do not know how the brain works that recognizes images. Hint, it doesn't work like an artificial neural network. But we do not know how those associations actually work, so we are at the moment working absolutely blindly. And here we cannot create something that will directly work on results we have. But in multiple other aspects, we can at least understand certain causal relationships. Why certain things influence each other. Like, for example, when we are diagnosing an electric motor about what's going on, then perhaps we can understand what elements influence the potential damage, what will cause, for example, the vibrations. Are vibrations caused by fault, or they are caused by normal operation? What influences that? Or does temperature of the motor cause the vibrations? Probably not. So these are certain issues that we'll try to cover during this course. I say try because so far I was not able to cover that, but I'm trying to rebuild this lecture into some more, let's say, working aspect. And another aspect of statistical models is that they are maximally transparent. So not only we can retrace what was the reasoning that caused our decision, but also we can understand what each aspect of the model does. So this is the big advantage of statistical models, that we really can explain everything that is going on in the model. What kind of assumptions were being made? We can even decode what implicit assumptions were being made. So, like, for example, we've assumed that certain behavior of, let's say, noise is with respect to certain distribution, or we assume certain information about ranges of variables. Those things we can retrace. We can critically assess what elements of models there are and what will be potential model limitations. So we already know starting when or what kind of subset we worked, or what kind of space we work, and where there are extensions outside of our area of expertise. So generally, statistical models and machine learning are very connected things to each other. And we'll, let's say, use a few minutes to explain those differences between them, because usually they are hard to distinguish from one another, and they are usually used to solve similar problems. Because we often are interested in classification or prediction, so those both approaches work for one another. However, the main point is that they should not be directly compared because they work for different things. And while we can say that machine learning is like a hacking solution to certain statistical problems to avoid modeling of probability distribution, because all machine learning models can be interpreted as some kind of statistical model. But there is a lot of heuristics, there are a lot of shortcuts that are being made to create machine learning models. But it doesn't make statistics superior, because machine learning often can solve problems, at least heuristically, which cannot be solved statistically at all. So, but on the other hand, when we can solve them statistically, we get much more from our solution than when we get it using the machine learning. For example, as I mentioned, uncertainty measures and stuff like that. So generally, if someone says that they compare the statistical model to machine learning model, they are doing something wrong, because they are, let's say, for different things. When we take a machine learning model, we generally want a number, classification, or being binary result, it belongs to this class or not, or we want a number of prediction of variable that we are interested in. Or, in case of modern machine learning models, we want generation of text, one text sample that will answer our question based on the prompt to the ChatGPT, right? Or some nice images of beavers you use using DALL-E, for example. So you get very limited one singular answer from what you want. In statistical model, we want to know about population behavior. We want to generalize, we want to know what kind of possibilities are available, what uncertainty about our prediction we have. Because while at the end of the day, we probably will need to use one number to make some kind of prediction, but still it would be nice to know how much error could happen one way or another. So those things are really for different goals, and that's why comparing them directly is counterproductive. So, to sum up a bit, statistical modeling, first of all, incorporates probability, which kind of makes sense because they're statistical models. Statistical models do not work on data itself. They work on entire data generating process. So when we create our model, we want to know how the data came from. Because what data is usually is not an actual value of phenomena that we are interested in, but it's a measurement of that. And this measurement could be obtained in multiple ways that obfuscated the actual result. For example, when we want to analyze political data using surveys, our data collection process is very limited because people do not like answering surveys. So we ask 1,000 people, and let's say 300 answer. And it is not necessarily random why certain people answer or not. Perhaps their answer, the lack of their answer comes with that because they're ashamed of their ideas. For example, they are related to age group because it was an internet survey and certain older people do not use this kind of social media. They were given this survey that often. So they haven't looked at their Facebook account for a month and they didn't see the survey, but it was reported. So we have the entire process of how data was collected, and that's only collection. Because we are interested what that person thinks. And we get from that what that person thinks by asking them a question, which they can answer truthfully or not. And this truthful answer, because again, they can be ashamed, they do not like the agency of which is asking the questions, they do not believe in surveys, they want to be edgy, whatever. So the answer doesn't have to be truthful. Worse, the answer not necessarily can be fully indicative, because we cannot get into someone's brain, we can ask them only questions. What is their preference? If there is a binary choice, will you vote for this candidate in election? This is a bit simpler, but again, what's the context? If we only have given two candidates to choose, this is easy. If there are multiple candidates to choose, then they have their order of preference. Also, there are aspects that are influencing their choices in different ways, which can happen later, they can depend on mood. So we have the entire data generating process that from the thought process of who I support to what I put into the survey and do I or do not answer the survey, there is a multiple very uncertain aspects. And in statistical modeling, we want to capture those uncertainty aspects, even by assigning certain probability how likely the answer is true. So, just to be clear, we want to do that, but it's not always possible. So if we put too much uncertainty in the model, we will not be able to get anything about it, because everything will be uncertain. But that's why assumptions are so important, because when you are able to define your assumptions clearly, then you know your model limitations even before it starts. So, generally in statistical models, we want to understand this data generation process, which happens for all kinds of data that we have, which if we look hard enough, we can realize what is really the problem happening there. Where is that what we are measuring is not what we really want to infer about. In statistical models, we look for interpretability, because that's why we want these uncertainty estimates. We want to know what kind of reasoning comes to everything. Those models are usually regression-based. Regression is a dirty word, really, because it does not explain everything, but has a lot of baggage that is being collected to multiple subjects that are using regression. Generally, it can be understood by certain type of curve fitting. And this curve fitting might be more or less complicated. Generally, we want to know how well our model corresponds to the data we have. And despite what can be seen in multiple, these models are not limited to linear regression. And they can be as complicated as we want, with the caveat that the more complicated it becomes, the more difficult it becomes to really estimate the parameters to get credible representation. On the other hand, in case of machine learning, we have certain aspects. First of all, while in machine learning, we do not have that big assumptions about structures or traditional parameters. In statistical model, we have a functional relationship between input data and predicted outputs in given some kind of function that has certain parameters. In case of machine learning, we are often working with hyperparameters, so something that is not directly interpretable as parameters, but give general possibilities of structure. When we are creating a decision tree, we are creating the number of leaves, number of levels of tree, etc. In case we're creating neural network, we can give number of layers, number of neurons, certain interconnection parameters, but we do not specify directly everything. It's being more or less implicit. And usually in machine learning, because this potential structure is very complicated, we work on very many parameters. We do not focus on the individual ones, because usually we work on data, so we are not working on a data generation process. We do not try to understand all the aspects. We work more on the data as it is. And because of not modeling the process, so not trying to understand certain aspects of it and where it comes from, as long as we have a lot of data, we can learn a lot about the model, and this very flexible structure of machine learning models allows you to reconstruct certain aspects in multiple ways. This flexibility can represent multiple things. When, for example, we are working on the popular now diffusion models, that creates nice pictures from text prompts. It is generally a heuristic solution to a probabilistic problem. Because if we understand a picture as a sample from a probability distribution, then creating samples for probability distribution becomes more and more complicated. And in order to get this distribution, we really need lots of flexibility that models. Okay, I see that it's not this point to discuss that. Either way, what are the advantages of machine learning? Because as I said, there are different problems, and machine learning works best when we have high signal-to-noise ratio. High signal-to-noise ratio means that generally observing your data, the important information is larger than disturbances. So it can, in case of, like, say, electrical measurements, we can understand that the main current that we are measuring is much, much larger than noise. We are measuring the current in amperes, and we have a noise in milliamperes. So this is a very high signal-to-noise ratio. Different signal-to-noise ratios, of a sort of high signal-to-noise ratio, are, for example, images. Because in image, even if the image is blurry, you still can observe those significant structural aspects, like, for example, are there people in this, or is a car, or something like that, okay? So the noise in the images is, the image processing is typically high signal-to-noise ratio. The same with speech recognition, except some very specific situation when you have identifiable strong disturbance signals, like actual audio noise that is happening, that, let's say, someone is working on a file driver or something like that in the background, so you can have problems with understanding the text. But same with language translation, because language has a lot of structure, and the noise in languages comes really from typos, which have certain understandable properties. And machine learning is generally good if black box is okay. If black box is okay, then we can use machine learning models, and we can, as they get a quick solution with certain very limited assumption and stuff. In case of general machine learning works also well in situations where there is a large data set with large numbers of features. And it's because of two ways. First of all, when we have a large data set with large number of features, those features not necessarily are that well understood. We don't necessarily, modeling all of them might be very complicated, time-consuming, and not necessarily justified. And machine learning model can handle that for us and can find a solution. Maybe not an optimal one, maybe with strong limitations about generalization on uncertainty behavior, but still it can arise a solution, and creating a full probability model of complicated multi-feature problem without any strong prior knowledge on structural properties might be impossible to solve infinite time. So that's the big issue. On the other hand, statistical models work rather well in small data sets, because in case of statistical models, we can compensate for lack of actual measurements by implementing our knowledge about the process. So if we know that certain things cannot happen, we can exclude them from the model directly. If we know that certain things are more likely because we had previous surveys or previous experience, then we can again put them into the model and compensate for what our data is like. And Statistical model provides us uncertainty estimates, so gives us the option of knowing what is the margin of error. Because generally in statistical models we can simulate potential outcomes, and from potential outcomes we can compute potential benefits or losses, and we can, using uncertainty of our prediction, we can get an uncertainty estimate of our cost, and we can make more informed decision. That, for example, from our model, if everything is okay, there is like an 80% chance of much financial gain. But on 10% there is limited gain, on 5% we get break even, and on another 5% we get losses of multiple grandeurs. So we can get a distribution of potential gains. So we can make, okay, what is the chance that we will get an answer? So this is the advantage of uncertainty estimates. As I said, statistical models are transparent, are more easily interpretable, so we know exactly what's going on, which might have important applications regarding legal issues. When we want to use some kind of banking solution or something like that, we need to provide something that will be able to answer how is what being done when it's being audited. And statistical models allow us to investigate influences of actual individual predictors, because it can allow us to get some kind of it allows us to get us, for example, being naturally generative model allows us to observe how the data would change if certain things would be changed. So this is the important advantage. I see that there is some issues with the slide at the font issue. Can I change it or not? That's the no. There's some kind of zoom out. Oh, no. Generally, I won't be breaking this slide, but generally, because it's not means that machine learning is better, is a better option for large vision data sets. But what is really important? To solve the same problem in some kind of way that's feasible, machine learning model will require from us more data. Because on the same data level, we just, using statistical model, we can squeeze all the information from the data, including the uncertainty. If we have small data sets in machine learning, our machine learning model can just give us prediction that makes no sense. And they do not generalize. So that's a big problem. However, statistical models needs interactions to be specified. While in machine learning, we can get those much more freely because of this adaptive structure generally of machine learning models like neural networks, where they can create their own connections, relationships, functional relationships that can be much more complicated, which again is good and is bad. If we know that something is not related to something else, not putting that relationship in a model can be very beneficial, because there are situations when including certain information to the model might be much more harmful than avoiding it. It's related to the causal analysis that generally adding information that is being directly influenced by something that we already added can create much more confusion that we would really want. But we will discuss it during the further part of the lectures. What was the final bullet was that machine learning usually is a better option when we want just a number. If someone wants us to give a number, perhaps going to, and these are not interested in any kind of uncertainty estimates because of reasons, then going for a statistical model might be just a waste of time. Because if the as I mentioned in my previous lecture on analyzing databases, business case is very, very important. If your work does not have a business justification, it shouldn't be done. You shouldn't be doing something that is just for fun. In case of work situation, you just need to adapt your methodology to the issues that is needed. So in case if you need numbers, don't bother with statistical models because you will lose much more time. Okay, so we use statistical model when uncertainty is important or when signal to noise ratio is low. So there is a lot of disturbance in what we are collecting. It might be unreliability, like in surveys. There might be some kind of biological measurements with large variance. For example, you have 16 patients and you need to model the relationship of illness on certain medication. And in that case, each of those is a very individual person. You have significant grouping behavior, that there are multiple groups that behave very differently and you need to handle that. Situation when there is no, the training data is not perfect, so you have problems with getting reliable training data for what you want, and you have to work with what you've got to get some kind of answer that will be possibly, if limited, at least we know how limited it is. We are interested in the isolation of particular variables effects, making some kind of counterfactual predictions, so predictions based on something that we haven't observed yet. Those are places that statistical models can be very helpful. Of course, smaller samples, as I mentioned, 16 patients, for example, or 5 experiments, because we cannot do more experiments, or 5 experiments using machine learning is very risky. So statistical model will be much more generalizable if you know what you are doing. And of course, interpretability. So again, we want to come back to why our decision was made, why we decided to fire this person. Because algorithm says so, and this algorithm says so because what? Because there are certain prediction aspects that we've modeled here. Okay, in case of machine learning, is opposite situation. When there is a high signal to noise ratio, then machine learning usually will work very well because it won't be confused by the randomness in the process. If we have a really lot of training data and representative training data, then machine learning also will be advantageous because this training data will include enough information about the entire process. The entire situation where we have enough data is a very good situation, and unfortunately it's rare. For example, when you want to create a diagnostic system for machinery, you can have a lot of data, but you can have a lot of data of healthy processes. And you won't have data about faults because faults happen rarely. And so you have very unbalanced set or data set, you have to handle that. As said, overall prediction is more important, the number is what we want. We can expect substantial nonlinearity that we cannot understand what is going on. This especially goes for image, sound, text recognition, where we really do not know what is the relationship, but we certainly know that it's not linear, then going for machine learning might be okay. Huge samples, because working with huge samples is not that easy in the case of statistical models, and we can accept the black box. If there's a black box, then the machine learning models are generally black boxes. We can modify it in multiple ways, but still, they are still black boxes.